I'm Paul Cosby. What you just saw was gravitational lensing. Gravitational lensing is the warping of light due to mass. Mass affects gravity. The more mass you have, the more gravitational pull you have. Gravity affects everything. Gravity affects time. Gravity affects mass, and gravity affects energy. Light is a form of energy. Light travels in small particles called photons. Photons are small groups of electromagnetic waves, which are emitted from an energy source such as a star and then are observed by our eyes. Similarly to how a star will bend the path of a comet, large celestial bodies also warp the paths of light. It's easy to imagine an object's path being warped by gravity, but it's almost impossible to comprehend light being warped by gravity. You really just have to see it with your eyes. Several photos have been taken by the Hubble telescope of gravitational lensing. Gravitational lensing has also been modeled in movies like 2014's Interstellar. This particular film was my inspiration for doing this project. One scene near the end really caught my attention when it displayed a black hole. A physicist, Kip Thorne, was the executive producer of the movie, and he made sure that all the physics were extremely accurate. He went to the special effects team and had his equations applied to computer models so that they could accurately simulate a black hole. They actually made discoveries based on the visual effects of this movie. Because I am fascinated with gravitational lensing myself, I actually created a way of simulating black holes on my own computer. I went into my three-dimensional effects simulator, which I use for my videos, and I made a specially curved mirror to reflect images of stars and galaxies so that I could simulate gravitational lensing. The effect is remarkable and allowed me to myself create that black hole effect. The reason the black hole looks like this is it's got a disk of gases around it. The gases appear to curve above and under the black hole because the light from behind the black hole is being warped over and under it. Because of this, if you were to go around the black hole, it would always look the same. You would never feel as if you're actually going around it. All of this tells us that gravitational lensing looks awesome. It can make celestial events appear multiple times, such as this quasar, 5 times shown in this image. It can distort background galaxies into shapes such as this smiley face. And it can also confuse scientists, right? Because it's just distorting our image of the universe. So how does that help? Actually, gravitational lensing helps us detect one certain thing: dark matter. Dark matter has mass, so it, like everything else, bends light. You bend light because you have mass. It's immeasurable, but it still happens. When cosmologists point telescopes into space and they see gravitational lensing, this is when they can tell that there might be dark matter. They can confirm that it's dark matter if they can prove that there's no other main source causing the gravitational lensing, such as a cluster of galaxies or a single galaxy. By learning where dark matter is, we can further understand it. We can further understand how it behaves with other matter. We can understand how and if we can interact with it. Maybe dark matter holds several key secrets to the universe. In summary, gravitational lensing is just one of those things that proves how awesome the universe is. It shows us what an effect gravity has on everything. Lastly, it is a reliable and crucial tool to understanding the composition of the universe. I'm Paul Cosby. If you liked this video, please consider subscribing to my YouTube channel, Guy Cow. One word, Guy Cow.